fundamentals of electrical circuits. And now we move on to again DC circuits, but still with dependent sources. When dependent sources are suggested or discussed, I find that students are generally a little nervous. But then dependent sources are better in the sense that they are dependent at a particular, they are dependent for their source value at a particular point, which means that it reduces the number of variables. So in that sense, let me hope that as we discuss the problems and as I walk you through the problems, you will be able to agree with me that dependent sources are a better bargain, no doubt about them. Okay, so let's look at some easy problems right now. Okay, so problem number 1. Okay, and as to the differences etc. in the concept, we'll discuss as we go along. Okay, so when you get a dependent source, immediately it becomes obvious to you because there would be what are called as rhombus kind of structures there. Okay, and then and that rhombus structure will tell you whether it's a dependent source, no doubt, but whether it's a current source or a voltage source. Okay, if an arrow is shown, it's a current source, and if just the signs plus and minus are shown, it's a voltage source. Okay, but the value is very important, and that's where you need to focus. Okay, so as you look at the problem, like for instance in this first problem, you see the sources first as usual. Okay, so one is an independent source which is 25 volt, the other is a dependent source, it's a current source, and the value is given as, its magnitude is given as 0.4 I. Immediately your attention should go to where this I can be found. Okay, so we see that the I is the current that is emerging from the 25 volt source. Okay, so once this is done, you can look at the other things. You see that there is a resistor R1, value is not given, but the voltage across it is given as 17 volt. That's a nice value, that's a nice figure. And then R2, again the ohmic value is not shown, but 14 amps is shown there. That's also a good value. Okay, but at the same time, we also already saw that an I comes from the left side and a 0.4 I comes from the right side from the source. The other is from both the sources. One is the independent, the other is the dependent source. And together, as per Kirchhoff's law, they flow together down down R2. Okay, or in other words, 1.4 I is equal to 14 amps, or I is equal to 10 amps. Okay, so immediately these things should follow. Now let's read the problem and continue. Okay, the power supplied by the 25 volt source in the figure shown below is what? Okay, so we need to find out I. That's all. Okay, because power supplied is equal to the voltage across the source multiplied by the current that pushes out. So 25 into 10, 250 volt. Okay. So the 2 points that you need to be very careful about with respect to dependent sources happens to be that focus your attention on the kind of dependent source. Okay, and then move on to finding out where it is dependent, or the location on which it is dependent. Okay, so once you have that, then just use Kirchhoff's laws. Kirchhoff's laws is the best bet for solving problems with dependent source. Okay, moving on to problem number 2. Here we see again the structure which is indicative of a dependent voltage source, and the magnitude is equal to 2I, and that I is coming from the input terminal. So this is just a circuit segment which has 2 resistors, 2 ohms and 4 ohms. And what is asked is the circuit shown is equivalent to a load. So what is a load? Load is equal to the voltage across it divided by the current through it. Okay, or current that flows into it. Okay, so I is already there. Now we need to find out the voltage across the circuit segment, which is equal to 4 ohm into whatever current flows through it. So I've shown an X there. So 4 into X. So 4x is the voltage and I is the current. So 4x by I would give you the load. Okay, so what is 4x? How do you do that? Okay, for that you again use Kirchhoff's voltage law. What does it mean? It tells us that the voltage across the 4 ohm resistor has to be balanced by the parallel branch, which comprises of both 2I as also 2 ohms through which a current flows, which is equal to I minus X. Okay, because X is flowing through the 4 ohm resistor. Okay, so now we are having, so balancing them together, we see that 4X is equal to 2I, which is a rise again when you look at the parallel branch, and then again the next rise is going to be, and that's why the plus sign etc. is given. And the next rise is given by 2 ohms into I minus X, or 2I minus 2X. Okay, so just solve it. So 6 is equal to 4I, and what we require is 4x. Okay, so find out 4x and 4x by I. Okay, so 4x by I is as easy as 8 by 3 ohms. Okay, so that's a different kind of problem, but still a very simple problem. Okay, moving on to problem 3. We see again the 3 sources of which 5i, the voltage source is the only dependent one, and this dependence is on the current that emerges from the 20 volt source. Okay, so 20 volt to amps sources, and then the 5i voltage source, okay, dependent voltage source. Okay, and we have 2 ohms and 3 ohms. Okay, and now what is asked out of us is the current I flowing in the circuit shown below in amperes. Okay, so we need to find out I as in the earlier question. So let's start. So what do we know? We know that I comes in. Okay, 2 amps joins the 2 ampere from the 2 ampere source joins it, and together they flow into the dependent source as equal to 2 plus I. Okay, so now we have the overall current distribution, and then we take the Kirchhoff's voltage law. Take it on the periphery or on the outside, because we don't know the voltage across 2 ampere source, but we know the voltage across 20 volt source, which is equal to 20. We know the voltage across 2 ohms, which is equal to 2I. We know the voltage across 3 ohms, which is equal to 3 into 2 plus I, or 6 plus 3I. And then we also know the voltage across the dependent source, which is equal to 5I. Okay, so putting them all together, 20 is equal to 20 is at the left end, and so you you go to the right end and pick up all the voltages. So you have 20 is equal to 2I plus 6 plus 3I plus 5I, or I would call it as 5I plus 6 plus 3I, that is 3 into 2 plus I plus 2I is equal to 20. Okay, so once you have that, you just solve that, and you see that we see that 10I is equal to 14, or I is equal to 1.4 amps. Very simple. Okay, so the current that emerges from the 20 volt source is equal to 1.4. Okay, so moving on to problem number 4. Okay, so here we see 70 volt source and a 4 V0 source, where 4V0 is the dependent source, and it's dependent on the voltage across the 10 kilo ohm resistor. What else is left? There's a 20 kilo ohm resistor as well, and there is a pair of terminals given by AB. Okay, and what is asked is find Thevenin's equivalent at terminals AB of the circuit. So what we should recall from our earlier experience happens to be that now A and B are open circuited. So whatever current that flows from the sources flows through both the resistors in series. Okay, because there is no provision for current to flow through A and B. Okay, through A to B. Okay, so we see that the same current, since it flows through 10 kilo ohms and 20 kilo ohms, I have marked them out to tell you that if V0 is the voltage across 10 kilo ohms, then the voltage across 20 kilo ohms has to be, because it's the same current, it has to be 2V0. Okay, so now we can balance again all the voltages, where 70 is equal to 4V0 plus 2V0 plus V0, or V0 plus 2V0 plus 4V0, or in other words, V0 is equal to 10 volt. As simple as that, because 70 is equal to 60. Okay, and now what is asked is, what is the Thevenin's voltage? Okay, so Thevenin's voltage means we have to deduct the voltage across 10 kilo ohms from 70 volts to obtain the voltage across AB. So 70 minus 10 into the V0 is 10, so 70 minus 10, which is equal to 60 kV. Okay, you can 60 volts. You can go from the other side also, because 4V0 means 4 into 10, 40, and then you have to add 2V0 also. So that's again 20. So that's again 60. Okay, so from either of the sides you will get the total voltage, which is the Thevenin's equivalent voltage across AB, because AB is open circuit. Okay, moving on to the 5th problem. I hope you are realizing that we are doing very simple problems, though if they are all dependent sources, and we use essentially mostly Kirchhoff's laws. Okay, Kirchhoff's voltage law and Kirchhoff's current law as applicable. We have also tried to avoid any voltage across current sources, because we don't know them. So that's the reason why we always go towards the voltage sources and the drops across the resistors. Okay, so moving on to 5th problem. Again, I suppose your attention has been called by the dependent current source right in the middle, which is equal to I2. Okay, and where is I2 coming from, or where is I2 dependent on? It's dependent on the current which flows through both the pair of 1 ohm resistors on the right. Okay, so we have I2, again I2 flowing to the right circuit. So it means that 2I2 has to flow from 2I2 has to flow from the 1 volt source, or from the left side, which is equal to I1 as shown here. Okay, so I1 is okay. So now what is asked is, in the circuit given, the current supplied by the battery, which is equal to I1. So it's very simple, Kirchhoff's current law. Okay, because I1 is equal to I2 plus I2 or 2I2. Okay, which we have already done. Okay, now we need to find out 2I2, or we need to find out I1. So how do you do that? We just simply balance the voltages across the resistors and the available in the independent voltage 1 volt. So 1 volt is equal to again 2I2 into 1. Okay, so direction etc. matches because current is flowing into the positive terminal in both cases. Okay, so we are having 2I2 plus 2I2, that is 4I2 is equal to 1, which means that 2I2, which is I1, is equal to 0.5 amps. Okay, very simple. Okay, very simple. Okay, moving on to the sixth problem. Okay, this is a little complex, but at the same time not so much. Okay, all the simple problems have been picked up for this first session in the fourth section of the circuit analysis that we're doing. Okay, so moving on to the sixth problem. I suppose you have already noticed that there's a voltage source 3I0. Okay, which is dependent, and I0 is the current that is flowing through the 1 ohm resistor. Okay, and then we have also another 10 volt source on the other side, which is independent, and there's a network of 1 ohm resistors. Okay, and what is asked is consider circuit shown in the figure, the Thevenin's equivalent resistance in ohms across PQ. So now we stand guard at PQ and we look into the circuit. Okay, so what do we need? Okay, so here we have to consider something. The Thevenin's equivalent resistance, when you have to find out, you have to take the ratio of Thevenin's voltage to Norton's current, or the open circuit voltage to a short circuit current, because the dependent sources do not reveal their internal resistance. Okay, it is dependent, so we can't say for sure that you can choose this. You can't replace it by either a short circuit or an open circuit. Short circuit for a voltage source and an open circuit for a current source, because it is not applicable. That rule does not apply. So always when it is a dependent source problem and when you are supposed to find out the Thevenin's equivalent resistance, remember to find out the Thevenin's voltage and also the current, the Norton's current or the short circuit current, and take the ratio of voltage to current, open circuit voltage to the short circuit current, and declare the Thevenin's resistance. Okay, so now we have two steps here. First we go for the Thevenin's open circuit voltage. Okay, or P and Q are open. If P and Q are open, then Thevenin's voltage is definitely I0, because I0 flows through 1 ohm and that's the voltage directly across PQ. Okay, so that's how you can start off from. Okay, and now we go for other things, like for instance, okay, so now we can balance the voltages. We can say that 10 volt is the same as equal to, okay, let's take the outer circuit. So we have a 3I0 voltage, which is of course oppositely directed, so it's minus 3I0 as far as voltage balance is concerned, and then we also have I0. Please recall the earlier directions that I gave you, wherein any resistance in parallel with the voltage circuit is irrelevant. You can remove it. Okay, you can remove it or you can disregard it. In this case, let us ignore it, and so we see that 10 volt is the same as equal to I0, which is a rise, but minus 3I0, which is a 3I0 with a negative sign, because it's a drop. If you look at, if you are trying to balance 10 volt with respect to the outer periphery on the right side. Okay, so the 1 ohm resistor across the 10 volt source is also ignored. Okay, and because it's an open circuit, we have a value for I0, which is the Thevenin's voltage. Okay, we also see that when you are looking for the Norton's current, short circuit the terminus PQ, and that the current is called as IN. The current that flows consequently is IN. And since PQ is short circuited, the 1 ohm resistor in parallel with it becomes shorted. Okay, or in other words, there is no current flow through I0. All the currents flow through the shorted terminus, shorted path between P and Q. Okay, so I0 equal to 0. What does it mean? It means that the voltage source that we show that is dependent on it, which is equal to 3I0, is also equal to 3 into 0, which is a short circuit. Okay, so only 10 volt is now applicable across the 1 ohm resistor across it, as also the other 1 ohm resistor, which is at the bottom and horizontally placed. Okay, so it seems as we realize that the current that is now flowing through is going to be equal to 10 by 1, which is equal to, okay, because any time the current will be equal to 10 amps. So we have the ratio of that is minus I0 we see is equal to 10 volt, or I0 is equal to I0, which is the I0 into 1, which is in the Thevenin's voltage. It's oppositely directed, that's all. It's equal to 10. So 10 by 10 is equal to 1 ohm. Okay, so Thevenin's equivalent resistance is equal to 1 ohm. Okay, so that's simple as that. Let's go. Okay, but of course, a little different from the previous problems. Okay, moving on to the seventh problem. Okay, we see the current source, okay, dependent current source Ix into 1.5. We see a voltage source 12 volt, okay, and we see that the dependence is on the current that flows through a 6 ohm resistor, okay. So, and the other resistors which are 10 ohms and 8 ohms, okay. So, if about 1.5 amperes, 1.5 Ix moves upward, then towards the right Ix flows and the rest flows to the left, okay, Kirchhoff's current law, okay. So we are having 0.5 Ix moving towards the okay, it's going to go into the 12 volt source, okay. So the directions are shown, and so the drops also will have will be shown, are shown accordingly, okay. So now what do we do? Okay, so now we have all the currents distributed. Now we can find out what is called as the Norton's current, wherein Norton's current is obtained by short circuit, okay. So that's what is asked in the circuit, the Norton's current through AB, okay. So we short AB and we try to find out the current there, okay. What's the current? 8 ohms is bypassed and Ix flows through it. So our job is to find out Ix. How do you do that? By again writing out the Kirchhoff's voltage law, Kirchhoff's current law and Kirchhoff's voltage law, as they can be applied one after another, and you can solve, okay. So how do you apply Kirchhoff's current voltage law? Where 12 volt is equated to, again there is no drop across the short, so AB is 0, and then we are having 6 into Ix, okay. The direction is appropriately taken into consideration, 6 into Ix, but 0.5 Ix is flowing through 10 ohms, so that is equal to 5 Ix, but at the same time the direction is it's a drop as far as as far as the right path is concerned. So we are having 6 Ix minus 5 Ix is equal to 12, or Ix is equal to 12, which is what is the Norton's current. So very simply we have solved the question, the problem number 7 as well, okay. So coming to this last problem in this session, in this section of DC circuits with dependent sources, let's have a look at the contents. As usual, we have the 3 VAB, the dependent source, its voltage source, and it depends upon the terminal voltage. Okay, terminal voltage as shown as A and B. Okay, and this actually these two terminals are where we consider the Thevenin's voltage as also the Norton's current if required. Okay. So VAB, we would talk about the voltage across AB, with A being more positive compared to B. Okay, so that's so the arrow. So I have drawn a picture there to show you what is VAB, which is the voltage across VAB, and the arrow is pointed towards A, where A is having more positive, having more positive potential. Okay, so moving on to other things, we have a 5 volt source, a 2 kilo ohms, and a 1 kilo ohm resistor. Okay, so all of them are required. Since VAB, okay, so we should have taken note of that. VAB is the so okay, so we know what is VAB, and now this VAB is also the voltage across 1 kilo ohms. Okay, so if VAB is the voltage across 1 kilo ohms, the current is given by VAB divided by 1 kilo ohms, or VAB milliamps. Okay, milliamps is not shown, that's all. Okay, so the current and the voltage have the same magnitudes. One is of course in volts, the other is of course in milliamps. Okay, so moving on to so this current. So of course let's read for the circuit given above the Thevenin's resistance. Okay, as mentioned before, then we have to find the Thevenin's resistance. You have to find the Thevenin's voltage and the Norton's current or the short circuit current, and take the ratio. Okay, so if you have to find out the Thevenin's resistance across the terminals A and B, let's see what the next question is. Perhaps it asks for the Thevenin's voltage. Okay, for the circuit given above, the Thevenin's voltage across the terminals A and B. Okay, so we have to find out the voltage across A and B. Okay, so what do? You open circuit. Okay, and then you see that the current that flows through the 3 VAB dependent voltage source and through 1 kilo ohms is going to be VAB milliamps. Okay, so if VAB milliamps is taken by 1 kilo ohm, it develops a VAB voltage across it, positive terminal as shown. Okay, and 3 VAB is also in tandem with it. They are in continuity. Okay, so across 2 kilo ohms, now we have 3 VAB plus VAB. Okay, the VAB across the 1 kilo ohm, there is 4 VAB. So if 4 VAB is the voltage across 2 kilo ohms, it takes 2 VAB milliamps. Okay, because it's 2 kilo ohms, so voltage divided by impedance or resistance, we get 2 VAB as the current. So now there are two branches of currents, 2 VAB through the 2 kilo ohms and 1 VAB through the 3 VAB dependent source and the 1 kilo ohm resistor. So together, now the source gives rise to a flow of current of 3 VAB to cater to both circuits. Okay, so this 3 VAB now flows through the 2 kilo ohms and creates a 6 volt there, because 2 kilo ohms multiplied by 3 VAB milliamps gives you 6 volts. Okay? 6 VAB volts there. Okay, and now so let's see. So to find out the Thevenin's voltage, we need to find out VAB. Okay, so now we have a small circuit in between where 5 volt is now across the two resistors, 2 kilo ohms with 4 VAB across it, and 6 VAB across the other 2 kilo ohms. So together 10 VAB. 4 and 6, 10 VAB gives you 5 volt, or VAB is the same as equal to 5 by 10, which is equal to 0.5 volt, which is answer D as shown in the second of the two problems in problem 8. Okay, so now now we need to find out the Norton's current. For that, let's short circuit A and B as shown, and so we see that the voltage VAB becomes equal to 0. Okay, because the short circuit has a voltage equal to 0 across it. Okay, which means that the voltage, the dependent voltage 3 VAB, the dependent voltage source 3 VAB also becomes shorted, or it becomes 0 voltage. Okay? So now we are having so now we are having a short circuit across 1 kilo ohms, and we are also having a short through the voltage source. So in total, what can be seen is that the 2 kilo ohms also gets shorted, or in other words, the current that emerges from 5 volt is going to be equal to 5 divided by 2 kilo ohms, or what is called as what is equal to 2.5 milliamps. Okay, so 2.5 milliamps now flows through the short circuit, and that becomes what is called as the Norton's current. Okay, so Thevenin's voltage is 0.5 divided by 2.5 milliamps gives you what is called as 0.2 kilo ohms, which is answer. Okay. Which is answer B. Okay, so in this manner, I hope through the slightly different problems that we have been addressing, you have got a feel for how easy the dependent sources problems are, especially because of the dependence. The dependence reduces the number of variables, so it's easy to do. Okay, so the 3 important things to remember happen to be that when you are looking at the problem, go straight for the dependent source. Okay, and as to where the dependence is, be focused on that. Okay, and that's point number 1. Thereafter, of course, having a good look at the circuit, go for either Kirchhoff's current law and Kirchhoff's voltage law. Put them all together. Okay, never find out the voltage across the current source because you don't know it, but you can have any kind of circuits, perhaps in the periphery or as a cluster or something like that. You can apply Kirchhoff's voltage law, which will be given by the independent voltage source and the other kinds of and the drops across the resistors. Okay, so put them all together, you can solve for whatever is required. Okay, third point that I would like to make clear is that whenever you have to find out the Thevenin's impedance or resistance, remember that you can't go for the resistance in the pattern that we have employed earlier. You always go for finding the Thevenin's voltage across the same terminals. Okay, and across the same terminals you short it and then find the Norton's current as well, and then take the ratio of Thevenin's voltage by Norton's current. That gives you the Thevenin's impedance. Okay, so that's what that's there, and mostly an application of Kirchhoff's laws will give you very easily the solutions, and this is almost a sure question. Okay, because dependent sources students seem to be a little wary of, but of course it's always going to be easy. Okay, so let's go to the next session soon enough.